Okay, so section 12.3 is concerned with rate laws, and rate laws are mathematical descriptions of how the rate of reaction depends upon the concentration of reactants. Before we get going though, we have to talk a little bit about the nature of chemical reactions and something that we haven't mentioned today. If I have a reaction where reactant A is converted into product B, what we haven't mentioned so far is that the reverse reaction, B getting converted into A, also occurs. And this is going to be important as we think about how we might go about deriving or figuring out what a rate law is for a chemical reaction. So here's a reaction. Again, we've just got reactant A being converted to products B. A is consumed as time goes on and reduces its concentration, and B is produced. So what we know is that the concentration of A is changing because it's being consumed by the forward reaction and it's being produced by the reverse reaction. So if I want to write a rate law for the reaction of A going to B, it's going to be complicated by the fact that there are actually two reactions going on. What's going to happen is, as this progresses, the concentration of A will go down, and so what that means is that the rate of the forward reaction will decrease. As the reaction progresses, the concentration of B will increase, and so the rate of the reverse reaction will increase, and the amount of A that is being produced by the reverse reaction will become more and more dominant. So this seems like it's impossible to decouple these two reactions, except for at T equals 0, what we know is that the concentration of B equals 0, and therefore the rate of the reverse reaction will not be happening at all because there is no reactant for that reverse reaction. So to avoid the complication of the reverse reaction, it's common practice to calculate what we call the initial rate, which is the instantaneous rate of the reaction when the reactants are first mixed, and for the reason for this is because then the concentration of our product will equal 0, and the rate of the reverse reaction will equal 0 as a result. So we'll almost always use initial rates to determine kinetic information, and in particular the rate law. So a lot of kinetic studies are aimed at figuring out what the rate law is. That is how the concentration of the reactants and the concentration of the products varies with time, and we want this expressed in terms of the initial concentrations of our reactants. So if I've got a general reaction where the lowercase letters indicate the stoichiometric coefficients and the uppercase letters indicate the things that are reacting and being produced, the rate law is of this form. The rate of the reaction will be equal to a constant, and we'll talk a little bit more about that later, multiplied, and then for every reactant we have a term here where we've got the concentration of the reactant and it's raised to some power. So we get one of those terms per reactant. So we know it's going to have this generic form. The questions that we had is what is the value of this K, and what are the values of M and N? Now you'll notice, and I want to make this clear, that I didn't put A and B here. These exponents that go in here are not related to the stoichiometric coefficients. So here we have it all kind of written out again, a little clearer. For a generic reaction, A reacting with B to give C and D, the rate of this reaction can be described by a rate law which has the form: the rate is equal to a constant multiplied by the concentration of our first reactant raised to some power multiplied by the concentration of our second reactant raised to some power. So K is referred to as the rate constant. And the interesting property of the rate constant is it isn't dependent on the concentration of our reactants or products. It is only dependent on the temperature. So K is a rate constant. It's a given for a particular reaction at a given temperature. The exponents that appear in the rate law, M and N in this case, are what are referred to as the reaction orders of the reactants A and B respectively. So every reactant will have its characteristic reaction order. Sometimes you'll be asked to give what is called the overall reaction order, which is the sum of all of the individual reaction orders for each reactant. So you do want to be a little bit careful when you're answering questions regarding reaction order, whether they're talking about an individual reactant or whether they're talking about the whole overall reaction order. So the question then becomes, how do you determine the reaction orders? So the first thing to recognize is that the reaction orders need to be found out by doing experiments. You have to do kinetics experiments to figure them out. They are not going to be related to the coefficients that are present in the balanced equation. Occasionally they're the same, but that's more of a fluke than a general rule. We want to use the initial rate because we're only interested in the forward reaction and we don't have a mechanism for decoupling the reverse reaction. So by using initial rates, we don't have to worry at all about the reverse reaction. So you're going to be given experimental data and you're going to be asked to turn it into a rate law. So there's a fairly standard way of doing this, of figuring out the reaction orders and also the rate constant. It's called the method of initial rates. And all method of initial rates problems are done the same way. You just have to recognize that it's a method of initial rates problem. A dead giveaway that it's probably a method of initial rates problem is one of the sets of data that you're going to be given will probably be labeled initial rate. So I'm going to give an example of one of these reactions where that are occurring in the atmosphere, and it's the reaction between O2 gas and nitrogen monoxide, which is a gas produced in the engine of your car, and these two guys react to form NO2, which is a pollutant and respiratory irritant. So we know that the rate law for this reaction is going to have the form: the rate is equal to the rate constant multiplied by the concentration of O2 raised to its reaction order multiplied by the concentration of NO raised to its reaction order. So how do we figure out what M and N are? So to find the reaction orders, what we're going to do is we're going to run a series of experiments. In two of these experiments, we'll have constant O2 and we're going to vary NO. And in that way, we will be able to see how the rate is affected by the concentration of NO. We're then going to run another two experiments where we have constant NO, but we vary O2, and that'll give us the reaction order of O2. So let's look at some data for this. So we've got three experiments here. And then we've got initial O2 concentration, initial NO concentration, and then here's the giveaway that it's an initial rates problem. We've got initial rate. And if you look at the first two problems, or the first two runs of this experiment, you will see that the O2 is constant, but the NO doubles. And then if you look at the first and third experiment, you'll see that the O2 doubles, but the NO stays the same. So what this means is that we can use experiments 1 and 2 to figure out the order of NO, and then we can use experiments 1 and 3 to figure out the order of O2. So that's what we're always doing. We're looking for experiments where the concentration of one thing stays constant while the other changes. And we need one of those sets of experiments for each reactant. So the rate of experiment 1 will be equal to the rate constant multiplied by the concentration of O2 in experiment 1 raised to some power m, multiplied by the concentration of NO in experiment 1 raised to the reaction order of NO. In experiment 2, the rate will be equal to the same rate constant multiplied by the concentration of O2 in experiment 2 raised to its reaction order. And then this is multiplied by the concentration of NO in experiment 2 raised to its reaction order. So now what I'm going to do is I'm going to take the rate in experiment 1 and I'm going to divide that by the rate in experiment 2. So here I've got this rate 1 divided by rate 2 equals, and then I've got the two expressions top and bottom. So there's a bunch of stuff that cancels out here. Remember, K is not dependent on the concentration, it's only dependent on the temperature, so that term cancels out. And the concentration of O2 is the same in experiment 1 and 2, so those terms cancel out as well. So all I'm left with is this. Now I can simplify this, and this is what I do in the next line. So here it is written out with all of the terms that I can cancelled out. I'm just going to pull n out there because both the top and bottom are raised to the power of n. So what I'm going to do now is a little trick. Is I'm going to take advantage of some log rules, and we do this whenever we want to solve for the exponent. So if I take the log of a to the n, that's actually equal to n log a. And you may or may not remember, but using this log rule is really cool. This is the way to go when you're trying to solve for an exponent, which is what we're trying to solve for in this case. So what I'm going to do now is I'm going to take logs of both sides of this guy. So log of rate 1 on rate 2 equals log of NO in 1 over NO in 2, all raised to the power of n. And then I apply my log rule, and I can bring the n out the front. And that's really cool because what it means is I can now solve for n just by division. So I'm going to divide both sides by that term there. So log of rate 1 over rate 2 divided by log of NO in experiment 1 over the concentration of NO in experiment 2. And I put all those numbers in, and what do I get? I got a 2. So I know that my rate law is going to be K O2 to the M. We're still trying to figure that out, but for NO, the rate order is 2. The reaction order is 2. Okay, so now we have to do the same thing for O2. We're going to choose, though, the experiments 1 and 3. So here we go. Rate of 1 equals that. Rate of 3 equals that. Take the ratio of the 2, and then some terms will cancel. So that gives me this, and then I'm going to take the exponent here and put it out the front. And then I take logs of both sides. I apply my log rule at this point. So that means I can bring the m out to the front there. And then I'm going to just solve by dividing both sides by this term. So I can solve for m. And when I do that, m turns out to be 1. So now I know that my exponent there beside the O2 is a 1. I haven't written it in. And the exponent that goes with the concentration of NO is 2. So I've got my rate law. So you don't have to do all of this. You're just going to do something like this. You're just going to go that the order is equal to the log of rate A over rate B divided by the log of, the concentration of your thing in reaction A over the concentration of your thing in reaction B. You're just going to skip to the end. You're not going to do all of that preliminary work there. You just have to identify the two reactions where the concentration of what you're interested in is varying, but the concentration of the other reactants is staying constant. Okay, so once you've got your rate law, you can now get K by substituting in data from one of your experiments. And I generally do experiment 1 by default. So what I've done here is my rate law. I'm going to reorganize and solve for K, and I'm going to use data from experiment 1 that was in my table. So here it is. The rate of the reaction experiment 1 was 3.21 by 10 to the minus 3 moles per liter per second. The concentration of O2 in experiment 1 was 1.1 by 10 to the minus 2 moles per liter. And then the concentration of NO in experiment 1 was 1.3 by 10 to the minus 2. And I have to square that to account for the fact that the NO, that term there, is squared. So when you do all of this, you suddenly realize that kind of figuring out the units is a little bit sort of complicated, right? The moles per liters cancels out, moles per liters, and then that leaves moles squared, liters to the minus 2 on the bottom line. So, okay, here are my units. Oh, here's my number with my units. But you realize that determining the units for K isn't always easy. That's a lot of dimensional analysis that could potentially go wrong. There are some general rules, though, that can kind of help you out with this. If you look at the overall reaction order, where you add together the reaction orders for the two things, which in our case, because it was first order in O2 and second order in NO, then the units of K, the generic way of figuring it out, it's the concentration raised to the power of 1 minus the reactant order, and then the time term is always time to the minus 1. So for us, it's going to be concentration raised to the power of 1 minus 3, and then it's time to the minus 1. And then you just have to think about what are my time units and what are my concentration units. And in our case, so that's going to be concentration to the minus 2, time to the minus 1. In our case, concentration was moles per liter. So our K was going to have units of moles to the minus 2, liters squared. And then our time was seconds, so that would be seconds to the minus 1. So you can kind of, if you just remember this little formula for doing it, then that kind of helps you out. First order reactions always have units of time to the minus 1. Zero order reactions is always concentration by time to the minus 1. Second order, it's concentration to the minus 1 times to the minus 1. This becomes really easy if you use molarity. So second order would just be molarity to the minus 1, perhaps seconds to the minus 1, depends on the time units. So that's kind of, keeps it a little simple. Anyway, you'll get very used to this as we go through looking at the rate constant and thinking about the overall order of the reaction. Okay. So something to point out is that seems a little bit complicated, but sometimes if you get lucky, you can actually kind of eyeball the reaction orders and save a little bit of time. So, looking at the reaction order of O2, I need to find two experiments where NO is staying the same. And that's going to be 1 and 3. And if I look at what happens to my concentration of O2 here, it doubles. And what that means is the rate is going to be multiplied by 2 to some power. And sometimes I can see very clearly what that power is. When I look here, the rate, it doubles, right? It comes pretty darn close to doubling. It's 6.42 would be exactly at doubling, but it's very close to doubling. So what that means is that I know that M is 1, that the reaction order with respect to O2 is 1. We say that the reaction is first order in O2. So let's kind of go on and do the same for NO. We need two experiments where the O2 is not changing, and that's going to be 1 and 2. And then when I look at what happens to my concentration of NO in those two experiments, it doubles. So I know that this guy is going to be multiplied by 2 raised to some power. And if I look here, I kind of wrote this in non-official scientific notation to illustrate this point. This rate here goes up by 4. How do I get 4? 2 to the 2. So I can identify, just by eyeballing it, that it is second order with respect to NO. So the rate equals K O2 to the 1. I can put that in if I want to. NO to the 2, and I just eyeballed that. And now I would go ahead and solve for K, and so that's just going to be the rate divided by the concentration of O2 times by the concentration of NO squared. And I normally do this for the first experiment that I'm given. If everybody does the first experiment, then we'll always have super consistent results. It shouldn't matter what experiment I use, because remember, the rate constant doesn't depend on the concentration, it only depends on the temperature.